Hello, today I will explain the constant current, constant voltage module using the LM2596 buck converter. Let's take a detailed look at the operation principle of the LM2596 and check it in action through a demonstration. In addition, a schematic diagram of this module is included, so I hope you will get a lot of information. Now let's look at the table of contents. First, I will introduce buck converter and LM2596. After that, I will explain the principle of operation of the adjustable type LM2596. Next, let's look at how to limit the amount of current, by configuring an additional circuit on the LM2596, which does not have a function of current limiting. Fourth, we will check how the constant current function works through a demonstration of lighting a 1-watt LED. The demonstration of driving an LED includes the problems you may encounter when using this module and how to solve them. Now, let's take a look at the LM2596. The LM2596 is called a buck converter, or it can also be called a step-down converter. The structure of the buck converter is as follows. As you can see, it operates by turning the switch connected between the input and the output on and off at regular intervals. Hence it is often called a switching regulator, and it is the reason that the output voltage is lower than the input voltage. In order to transfer energy while the switch is turned off, storage elements such as inductor and capacitor are required. Unlike a linear regulator, it does not consume heat, so the efficiency may be very high, up to 90% or more. The LM2596 adjustable version is capable of supplying 3 ampere of current. And the input voltage range is from 4.5 to 40 volts. Output can be generated from 1.23 volts, the internal reference voltage, up to 40 volts. The formula for generating the output voltage is as shown here. It is calculated using the resistors connected to the feedback pin of the LM2596. Usually, R1 is fixed at a value between 240 and 1.5 kΩ, and R2 is adjusted to set the output voltage. As you can see from the formula, the value of R2 has a direct proportionality to the output voltage. Then, we will look at the internal structure of the adjustable type LM2596 and review the operating principle of the LM2596. Inside the LM2596, a 1.235 volts reference is generated and supplied to the positive port of the differential amplifier. An external feedback pin is connected to the negative port of this differential amplifier. So, when the value of R2 increases, the voltage applied to the feedback decreases. This will bring a rise in the output of the differential amplifier. Please note that the differential amplifier is an amplifier that amplifies the voltage difference between the positive and negative ports. That is, the voltage difference between feedback and internal 1.235 volts reference will be amplified by the differential amplifier. The next stage is a comparator, and an oscillator with a frequency of 150 kHz is connected to the negative port. I'm not sure that the oscillator output waveform is actually a sawtooth shape as shown in the diagram, but considering that the comparator output is used to turn on, off the transistor, it seems reasonable to see it as a sawtooth waveform. The differential amplifier output is connected to the positive pole. Therefore, when the voltage of the positive pole increases, the length of the pulse corresponding to high becomes longer and the length of the pulse corresponding to low becomes shorter. In addition, when the voltage of the positive pole decreases, the length of the pulse corresponding to high becomes shorter and the pulse length corresponding to low becomes longer. This pulse turns on and off the transistor connected to the output. The longer the high pulse, the longer the transistor is on, so the output voltage rises. The longer the low pulse, the shorter the time the transistor is on, so the output voltage will drop. Because of this principle, when R2 rises, the feedback voltage decreases and the output voltage rises. The opposite also applies. According to what we saw on the previous page, this device could only control the output voltage through the feedback pin. So, how can the LM2596 module control the current? It is possible through the extra circuitry as shown in the schematic right here. Let's take a look at each part. First is the voltage control block. It is composed of 2 resistors R1 and R2 on the previous page when we explained the operation of LM2596 IC. The output voltage could be adjusted by changing the resistance values of R1 and R2. There is a potentiometer at the R2 position, so the output voltage can be adjusted. Turning the potentiometer knob clockwise increases the output voltage and counterclockwise decreases the output voltage. Next, let's look at the current control. It corresponds to this part. First, the 78L05 LDO receives the input voltage and generates 5 volts. It is due to this LDO that this module requires at least 7 volts of input. This voltage is connected to the supply power of LM358 operational amplifier, and is used to generate a reference voltage of 2.5 volts for the TL431. The 2.5 volts is voltage divided by a resistor and a potentiometer, to be supplied to the negative port of the LM358. The positive port of the LM358 is connected to the negative port of the output terminal. What you need to note here is this 0.05 ohm resistor connected between the negative of the output terminal and the ground of the module. When the current supplied to the load increases, a voltage drop occurs through this resistor due to the return current, resulting a potential difference compared to the ground of the module. As the current increases, this potential difference rises. And when it is higher than the voltage connected to the negative port, in this case, the voltage divided by 2.5 volts, the output of the LM358 is driven and it is supplied to the feedback of the LM2596 via the diode. At this point, the output of the LM358 becomes dominant, so even if R2 is increased to increase the voltage does not increase, preventing further current rise. The input voltage range of the LM2596 module is 7 to 30 volts, and as mentioned before, this is a limitation of 78L05 used inside the module. Now, I will show you a demonstration of driving a 1-watt LED using the LM2596 CC CV Module. The 1-watt LED used in the demo is a deep red LED with a rated voltage of 2 to 2.2 volts and a current of 300 to 350 mA as shown below. Before connecting the LED, to protect the device, set the voltage and current control potentiometer knob to the minimum value by turning it counterclockwise until you hear a click sound. Then set the output to 2 volts by turning the voltage potentiometer knob clockwise, which is the rated voltage of the LED. Next, put the multimeter in the current measurement mode, and move the red terminal to the current measurement position. You can see there is almost no current flowing because the current control potentiometer was initially set to a minimum. Now, let's rotate the current control potentiometer clockwise so that it is 300 mA. We are now ready to connect the LED. In order to read the current, I connected an INA219 current sensor between the LM2596 module and the LED. I can read both voltage and current from the INA219, but my breadboard connection is not very good and the voltage reading is not accurate, so I'll just refer to the current from the INA219 and check the voltage with a multimeter. Now, let's connect the power. When I connect the power, you can see that the LED is dimly lighted, and the voltage value at both ends of the LED is only 1.7 volts, less than the 2 volts which we set earlier. It seems odd that the voltage is dropping with such an amount at the load, since the LM2596 performs output regulation by monitoring the feedback input. To see why, let's take a moment to look at the circuit diagram we looked at. If you look closely at the output terminal, you can see that there is a diode at the output terminal to prevent reverse voltage, and the feedback is connected between the diode and the output terminal. Therefore, the LM2596 is regulating the voltage before the diode, not the output terminal, so the voltage drop due to the diode cannot be compensated. Since there is no possibility of inflow of reverse voltage except for the application that charges the battery, you can remove this diode, but in this demonstration, we will compensate for the voltage drop of the diode by increasing the voltage applied to the LED. By turning the knob clockwise, now, the voltage applied to the LED is 2 volts and you can see that the LED is much brighter. 157 mA is flowing at the LED forward voltage of 2 volts. The relationship between the voltage and current of the LED is characterized by the IV characteristic. As the forward voltage increases, the amount of current increases as well. Then, let's increase the forward voltage to see the CC function of LM2596. As the voltage increases, the current increases and then saturates at 304 mA, maintaining the voltage and current at 2.172 volts and 304 mA respectively. In this state, the voltage and current will not increase even if the voltage potentiometer knob is further turned clockwise. Finally, let's look at the change in the output of the LM358 connected to the feedback. Before reaching the current limit, the voltage is 0 volts. In this state, the output voltage can be controlled only by the voltage control potentiometer. If you increase the amount of current flowing through the LED by increasing the output voltage, the LM358 output drives 1.8 volts at some point. It is this moment when the current limit is reached, and from this point, the feedback is controlled by the LM358. Now, let's summarize what we learned today. Buck converter is a switching type step-down regulator and the output voltage is lower than the input voltage. Output voltage of the adjustable type regulator is adjustable by changing the value of the resistors connected to the feedback input. Basically, the LM2596 can only control the output voltage, but the amount of current can be controlled by configuring an additional circuit. You can drive the LED or charge the battery by limiting the amount of current. Also, it can be used to maximize the efficiency of solar panel. This is it. Hope you have earned a lot watching this video. Thank you for watching. Have a good day.